All right, so in the previous video, we've talked about the application of crystallographic planes to body center cubic and simple unit structures or simple cubic structures. In this video, we are going to be talking about determining the atomic packing factor and coordination number for the face-centered cubic structure. Now, what's the face-centered cubic structure? Let's draw a simple cube to represent that. Okay, so we have a simple cube. All right, we have a simple cube. Okay, each of these corners contains corner atoms. We have corner atoms, we have corner atoms, and we have corner atoms on each corner. Now, the word is said face-centered cubic, which means on each face of this cube, we have an atom. So we have here, on each this particular face, we have this particular atom. Okay, so directly opposite this face, which is this other face now, we also have a central atom. On this other face itself, we have a central atom as well. And directly opposite this face, which is behind now, we also have a central atom. Okay, whereas on this other upper face, we have a central atom. And directly opposite it, which is the bottom now, we also have a central atom. So these central atoms connect. We have this to this, and we have this connecting to this, something like this. So this is called the face-centered cubic structure. So if you pick a pictorial view of or a one-dimensional view of this, let's just get a one view picture of what it looks like. We'll have something like this. Okay, so we have the corner atoms, and we have the corner atoms. Now on each of these face, we have a central atom. So if there was another face attached up here, let's see something like this. It means that just like we have the corner atoms here, we have the corner atoms here, we have the corner atoms here and here as well. On this face as well, we have another what central atom connected here. If we also draw for this other side, okay, we have here corner atoms and corner atoms, corner atoms and corner atoms. On each of these faces, we have central atoms situated, something like this. Okay, so this is just like a 1D view. Okay, this is like a three-dimensional view. Now, these corner atoms are actually being shared. The one on this face and the one on this face is not completely one atom. We just have we have two atoms which are actually what sharing. So which means this is bringing half and this is bringing half. Both of them completely makes up a complete atom. So these two atoms are sharing. These other atoms on this face, this and this are also sharing. So both of them completely gives us one atom individually. Same thing with this other central atom. This and this are also sharing. So both of them completely mix out one complete atom. So in general, in the central atoms, you have up to 1, 2, 3, 4, 5, 6. But these six atoms are actually what? Not six atoms in general. It means that these six atoms are sharing. This phase is sharing with this phase to produce one. So six of them simply become 6 multiplied by what? 1 all over 2, which actually gives us a 3 complete central atom. So which means this phase is producing half, this phase produces half. We have one complete atom between these two phases. This phase produces half, this also produces half. So we have one complete atom between these two. This produces half and this other phase produces half. We also have one complete atom. That gives us 6 times 1 over 2, which is actually what? 3 central atoms. So for the face center cubic, we have 3 central atoms. Now we talked about coordination number, and we said coordination number is simply the total number of atoms being shared by each of the central atoms. So this particular central atom, okay, let's pick out one face and analyze that definition. All right, so let's consider the up plate, okay, in this manner. All right, so this is the upper face now. These are the corner atoms, these are the corner atoms, these are the corner atoms, and these are the corner atoms. So we have a central atom. This central atom and the one behind or the one under, both of them completely forms a complete what? Atom. So this is producing half central atom, this is producing half central atom, and the both of them gives us a complete atom at the center. All right, so we have 1, 2, 3, four corner atoms here. So each of these atoms, of course, are also sharing half. Okay, sharing with these atoms now, all corner atoms. So we have that the central atoms are sharing what? Total number of four atoms. Each of these central atoms now are sharing total number of four atoms. All right, so now we have three faces. We have the first face for the cube, which is up and down. These two faces, or the atoms on the center of these two faces, are sharing what? Four corner atoms. Or okay, they are sharing four corner atoms. So keep that aside. The upper face shares four corner atoms. This other face and this other face are also sharing, makes a complete what? Central atom. This brings out and this brings out, they make a complete central atom, which means, and this other atom are also what? Sharing four corner atoms, just like the upper face. So the side face also shares four corner atoms. And finally, the forward face and the inner face now, this particular face and this particular face also makes a complete what? Central atom. This brings halves and this brings halves, and these space are also sharing what? Four corner atoms. So we have total number of four. So if you add them up, 4 plus 4 plus 4 gives us what? 12 atoms. So which means, by definition of coordination number, the total number which a central atom shares, or total number of atoms which a central atom shares, becomes the coordination number. Hence, the face center cubic structure has coordination number of what? 12, because each of these atoms, each of these central atoms are sharing what? 4 atoms on each face. Therefore, the coordination number, okay, for the face center cubic structure, which is FCC, is simply equal to 12. So we have its coordination number to be 12. All right. So having talked about the coordination number, the next thing we talked about in the previous videos are what? Atomic packing factors. I said these two terms are very key or important terms talking about crystallographic planes, coordination number, and the atomic packing factor. So I said that atomic packing factor tells us the percentage of, okay, percentage of volume or space which an atom occupies in a cube. And mathematically, we have atomic packing factor to be equal to the number of atoms producing volume multiplied by the volume of the atoms itself, all over the volume of a cube. Okay, all over the volume of a cube. Now we are talking about a face-centered cubic, structure, and we've said that for a face-centered cubic structure, each atoms or each of these faces contains a body, a central atom. For each of the faces, they are always what? A central atom. So which means the closely packed regions can take place on each of these faces. So this can be from here to here. This can also be from here, okay, from here to here. This can also be from here to here. So which means on each of these faces, we can have a closely packed region. So which all the atoms can always what? Come in contact with the central atom for face center cubic. So it's simply something like this. Let's say we have, okay, it was explained here earlier. So this particular atom, of course, can come in contact with the central atom. All the atoms on this face can come in contact with the central atom. All the atoms on this face can also come in contact with the central atom. So which means their closely packed regions can always be from, okay, diagonally. This is diagonal for each of the faces. We can also have this to be diagonally for each of the faces, and this can also be diagonal for each of the faces. So simply pick out one of the diagonals. If you pick out one of the diagonals to analyze for atomic packing factor, pick out one of the diagonals to analyze for the atomic packing factor. Okay, this is my formula. Number of atoms multiplied by the volume of atoms. Okay, this is now volume of cube. All right, so pick out one of the diagonals and analyze for the structure. Let's pick out this diagonal. We have something like this. Okay, but not forgetting on this face, remember from here to this point is a radius, and from here to this point is also a radius, and distance between these two atom corner atoms is what we call the lattice parameter or the lattice constant, which we give in the previous videos as simply a, and we said a is equal to what? The sum of these two radiuses, r plus r, which gave us 2r. But then if you have split this into two, notice that this corner atoms has a radius, but this particular central atom has been divided into two, which means it has a diameter and not a radius. And diameter is simply what? 2 radius. So which means on this face, you have, okay, we have a radius, and here you have a radius, while this becomes the sum of two radius, which is now diameter. Okay, so radius plus 2r plus r simply gives us 4 radius. That means we have on this diagonal face now, we have something like this. This becomes 4 times radius, which is total value of the diagonal, r plus 2r plus r, and that simply gives you 4r. So you have this. Okay, now not forgetting that the atoms or the corner atoms are separated by a distance of what? A, since it's a cube. And this A simply represents what? The lattice parameter. So which means this spacing is A, also the height remains A for a cube. So call here A, B, and C. Let's now find the relationship between the lattice parameter and of course the radius itself. So from Pythagoras theorem, we know that the square of the hypotenuse arm from Pythagoras theorem, A, B all squared, is equal to the sum of the square of the both adjacent sides. Okay, this is AC squared for the hypotenuse arm. So you have AC squared equals AB squared plus, of course, BC all squared. All right, so you have this. So this implies now that AC squared, we already know that AC is simply what? 4r. So AC squared becomes 4r all squared. And this is equal to, we said, AB squared, and AB simply what? A. So this is now A squared plus, we also said BC squared, and BC is also A. That becomes A all squared. So 4r squared is equal to A squared plus A squared obviously gives us 2A all squared. Alright, so this now implies that, take note now, I want to make A subject of the formula, so I can simply keep, okay, if I expand this, 4 squared gives me 16, r squared gives me r squared, and this is equal to 2A all squared. So I have this. Okay, so I have this. All right, so 16 r squared is now equal to 2A squared. I want to make a subject of the formula. This now implies that A squared is equal to, divide both sides by 2. It becomes 16 r squared all over 2, and A squared is equal to 16 divided by 2 obviously gives you 8. So you have 8r squared. But I want to make a subject. All I do now is simply what? Take the square root of both sides to make A the subject of the formula. And therefore, A becomes square root of 8r all squared. Okay? Therefore, A is now equal to, the square root of 8 is simply going to be 2 root 2, and of course square root of r squared will simply give me r. So it is fair to say, in order to avoid an error here, this is fair to say 2r root 2. So this becomes the value of A. All right, so this is now the relationship between the lattice parameter and the radius of the atom itself. So A is simply equal to 2r times root 2. Now, if you have this, we want to find the atomic packing factor. Okay, we want to find the atomic packing factor for a face-centered cubic structure. I think I can take this off now. All right, so we want to find the atomic packing factor, APF, for FCC, and we said the formula remains number of atoms, okay, which contributes their volume multiplied by the volume of the atoms involved, all over volume of a cube, because the atoms are evenly spaced on a cube. So let me draw back the face-centered cubic structure. Okay, Let me draw back the face center cubic structure. All right, so we had this. So we said each corner, of course, each corners contain atoms. So we have each corner atoms. Each corner contains atoms, and each of the face also contains an atom, so which is why it is called the face center cubic. So on this face we have an atom at the center, and directly opposite the face, which is this, we also have another atom at the center, and these two atoms are what sharing to become completely one. So this brings half of its volume, this brings half of its volume, both of them combine to become one. Also, we have here on this face, we have a central atom, and directly opposite the face, which is behind there, we also have a central atom, and the both of them also shares to make a complete, to give a complete volume. So this is bringing half, this is bringing half, both of them brings complete volume one. And finally, on this particular face now, on this face, we have a central atom, and the face behind as well, which is this face behind, we also have another central atom, and the both of them combine to bring one atom. So which means these six atoms, we have 1, 2, 3, 4, 5, 6 central atoms, but these six central atoms are not six completely. Why? Because they are all producing what, half of their what volumes. So this is half, which is one. So six of them is simply 1 all over 2 multiplied by 6, and that's simply what, equal to 3. So in general, we have three central atoms. In total, we have three central atoms. This is half, this is half, both of them produce 1. This is half, both of them produce 1, which is 2. This is half, both of them produce 1, which is also 3. So it means we have 1 over 2 times 6, and that gives us 3 central atoms. So number of central atoms now equals 1 all over 2 multiplied by 6, and that gives us 3 central atoms. Then again, we need to find the total number of corner atoms. Remember I said that each of these corner atoms contribute 1/8 of their volume. This also contributes 1/8 of its volume. The entire corner atoms contribute 1/8 of their volume. And the total corner atoms we have here are 1, 2, 3, 4, 5, 6, 7, 8 corner atoms, and each of them are contributing 1/8 of their volume. Therefore, number of corner atoms equals 1 all over 8 multiplied by 8, and that's simply equal to 1. Hence, the total number of atoms contributing volumes, which gives us n atoms here. Therefore, n atoms, number of atoms contributing their volume becomes number of central atom, which is 3. So we have 3 plus number of corner atoms, which is 1, plus 1. And n atoms equals 3 plus 1, which is 4. So we simply have number of atoms to be 4. Now, the volume of atom itself, okay, volume of atoms, of course, the volume of atoms is the volume of a sphere, because all atoms are spherical in nature. So they take the volume of a sphere, and volume of a sphere is simply 4 all over 3 pi r cube. So they become the volume of the atom. So the next thing to find out is the volume of the cube. We've now found relationship between the lattice parameter of the cube and the radius of the atoms, and we said A is equal to 2r root 2. So all we need to do now is simply find the volume of the cube, and we know that volume of a cube, V, is simply what, the cube of all the sides. And if the sides are separated by a distance of a, that means volume becomes a to the power of 3. And we know what a is. A is simply this value. So we simply compute the volume of that cube. Alright, so a, V is simply equal to a to the power of 3, and a is equal to this 2r root 2. So you simply have 2r root 2 all to the power of 3. Okay, and this is now equal to 2 to the power of 3 is 8. R to the power of 3 is r cube. Then we'll compute 2 root 2. sorry, we'll compute root 2 all to the power of 3. Okay, we have this, so I can leave it like this. So if we substitute these whole values into the formula for atomic packing factor, we are going to find out that the atomic packing factor, APF, for a face-centered cubic, we said, is equal to number of atoms contributing volume, and that number of atoms is 4. So we have here 4 multiplied by the volume of atoms. Volume of atom is a cube, which which is is a sphere, which is 4 over 3 pi r cube. So we have here times 4 all over 3 pi r cube all over, we said the volume of cube itself, and we've obtained the volume of cube as this. So this is now 8 r cube multiplied by root 2 to the power of 3. So take note, you might wish to expand, of course, root 2 to the power of 3 multiplied by 8. You're free to do that, but I choose to keep my workings like this, okay, for a reason. But then from here, notice now that arrow cube can strike arrow cube, and also 4 here can go here, and it's 1, 4 can go into 8, and that will give me 2, which means I have at the numerator now, what I have left is simply 4 all over 3 times pi. I have 4 over 3 pi all over, here I have 2, okay, I have here 2 times root 2 to the power of 3. Okay, so you might wish to want to expand this value at this point, or you can still proceed to solve, but I choose to proceed to solve here. All right, so atomic packing factor, APF, is now equal to, at this point I need to convert this division to multiplication. I simply employ my board mass. I will simply have 4 all over 3 pi multiply, converting this now to multiplication, and I have to now invert this denominator. It becomes 1 all over 2, okay, root 2 to the power of 3. So from here, 2 can also strike 4 here. 2 goes into 2 is 1, 2 goes into 4 here is 2. So this is now equal to, that means at the numerator now, I'm left with 2 pi. I have 2 pi all over, and at the denominator, I'm left with 3 times root 2 to the power of 3. This becomes 3 root 2 to the power of 3. All right, so let's evaluate everything at this point. Atomic packing factor, APF, is now equal to, let's obtain 2 pi. All right, so 2 pi gives us 6.283 all over. Let's also obtain 3 multiplies root 2 to the power of 3. Okay, so I'll first of all compute root 2 to the power of 3. All right, so 3 multiplies root 2 to the power of 3 simply gives me 8.49. 8.49. All right, so at this point I will divide 6.283 into by 8.49. 6.283 divides 8.49, and I obtain here to be 0.74. So this simply implies that atomic packing factor by percentage, I will simply multiply this by 100, and I will obtain it to be 74%. So the atomic packing factor for a face center cubic is given as 74%. All right, guys, so that's how you find atomic packing factor for a face center cubic structure. In the next video, we'll talk about the hexagonal close pack structure. I think I'll pause the video here. Okay, so I will see you in that video. Thanks and cheers.